So let's bump it up here. We've gone from linear functions to quadratic functions. Now let's go ahead and raise our powers to include what we would now just call polynomial functions. Anything that's linear or quadratic or has a power that is higher than 2 would still fit into this category, but we really want to more focus on the non-quadratic polynomial functions and the non-linear ones. Like the linear and the quadratic, those have nice stuff that's very specific to each of them. And that's where that kind of level of specificity ends. We can't really talk about how cubic stuff that has power 3 functions, cubic functions, really all end up looking and working, and there's as it turns out, way too much different stuff that can happen. So broadly speaking, what else can we really talk about? Well, some of it we come back around to. We have mentioned before this idea of a ZERO, so we're bringing that back in again. That is a number that if we plug it into our polynomial function, we would get 0, which means that that's part of an x-intercept. And we said x-intercepts were of interest to us, generally speaking. Now, there also happens to be a little extra algebra going on that's kind of tied in with the business of a ZERO, and that's what we call the Remainder Theorem. So there's a way of trying to rewrite polynomials. So there's a nice little expression, x minus c. There's a quotient. And if there is a remainder left over, well, there it is. What we're really and truly interested in would be when that remainder is 0. When that remainder is 0. That's what we'd be interested in, because that would give us at least a linear factor. X minus c would be a linear expression that is a factor of our polynomial. So we would really dig that. That's the factor theorem. If x equals c is a ZERO, then that means x minus c is a factor. And vice versa. If I know that x minus c is a factor, that means x equals c is a ZERO. And we've already been using that idea when we talk about factoring quadratics and getting x-intercepts. Hey, we've already been doing that. Now we're taking that and kind of boosting its usefulness. So if x equals c is a ZERO, that means you plug that number in to your function, you get 0, aka 0 remainder. That also means x minus c is a factor of your polynomial. Synthetic division ends up being a super helpful way for us to try to test this out. If we get a remainder other than 0, then we do not have that ZERO. We would not be able to build a nice little factor. So we want to make sure that we go through a little quick reminder about that synthetic division. So let's say that we have been given this x value, x equals 1/2. And we're being told it's a ZERO. So we know how this synthetic division should work out. It should work out 0 remainder. So we're going to take the coefficients, the 2, the 1, the -13, the +6. We're going to put those in to our synthetic division structure. We're going to have that x equals 1/2 out in front. We're going to take the 2 and immediately drop it all the way down. Now, the bottom number times the number out front go in the next blank. So underneath of the 1, we get a 1. We add down the columns. 1 plus 1 is 2. The most recent number on the bottom times the number out in front. 2 times 1/2 is 1. Add down the columns. We get a -12. Take that -12 times the 1/2 out front. We get a -6. add down the columns, we get that 0. That is the last entry. That is our remainder. Our remainder is 0. So yes, we have been told true that x equals 1/2 is a ZERO. That means, again, x minus 1/2 is a factor. They're asking us to find all of the zeros, the ZEROs, though. So we're not so much worried about the factors as we are worried about the ZEROs. That string of numbers at the bottom with the 2, the negative 12, and the remainder of 0 mean that the 2, and the negative 12 give us our quotient. Sorry, that wasn't peeking up already there. So our quotient, if 0 is the remainder, negative 12 is the constant term, 2x would be the regular x term, and 2x squared would be our x squared term. And so with the 2 being a positive and the other 2 being a positive, there's our quotient. We've got a quotient that's now quadratic. We can take that quadratic expression, set that sucker equal to 0, and find the other ZEROs. As it happens, this factors. We've got a factor of 2 that we can pull out, and then we can factor the x squared plus x minus 6. Set each factor equal to 0, and that gives us the other ZEROs that they asked us to find. X equals negative 3, x equals positive 2. Now, we do want to make a couple of side notes here. Since we've mentioned these other relationships, let's just go ahead and mention those in more detail for this example. If they told us that x equals 1/2 is a ZERO, x minus 1/2 is a factor. If we have discovered x equals negative 3 was a ZERO, we found that that directly came from factoring. So x plus 3 is a factor. Same for the x equals 2 is a ZERO, came from the factor x minus 2. But we also have that 2 that we factored out a little bit ago, and that needs to be in there as well. Otherwise, we don't have a correct matchup between our factor stuff and that original function that they gave us. So there's a little bit of sneakiness. We don't want to forget if we factor out a number somewhere along the way. Each of our ZEROs is tied to an x-intercept. The one that they gave us, x equals 1/2, means we have an x-intercept, 1/2, 0. The other ones we found, a ZERO, x equals negative 3, means that we have an x-intercept, negative 3, 0, and a ZERO of x equals 2 means that we have an x-intercept of 2, 0. We want to know about other kinds of relationships that there might be going on that have some sort of helpful use to us as far as the functions, as far as graphing. So we do want to look a little bit more into what else is going on other than the ZEROs. What else is there? Other than the relationship between ZEROs and factors, what else is there? Now, brought up some, shrink it back down again. Let's just do a quick little bit of the synthetic division stuff together. Similar kind of example. Here is x equals negative 2/3. We are being told it's a ZERO of this g of x function. G of x equals 3x squared minus 25x, g of x is equal to 3x cubed minus 25x squared plus 21x plus 26. We're taking those coefficients, 3, negative 25, 21, and 26. We're putting those into our synthetic division setup. Out in front is that ZERO number that they told us, negative 2/3. The 3 drops all the way down directly. I take the number on the bottom times the number out front. 3 times negative 2/3 is negative 2. That's going to go into this empty spot underneath the negative 25. So I put a negative 2 in there. Then I add down the columns. Negative 2 plus negative 25 gives us negative 27. Negative 27 times the negative 2/3 out front. That's going to get us a negative 18, excuse me, or positive 18. We're going to add down the columns. 21 plus 18 is going to give us 39. We're going to take that most recent number on the bottom, 39 times the number out front, negative 2/3. That's going to give us a negative 26. We're going to add down the columns, and we're going to get that remainder of 0 that we were expecting. We're expecting a remainder of 0 because they told us x equals negative 2/3 is a ZERO. I am expecting a 0 remainder. So there's some nice kind of tied in relationships that work to our advantage. If I didn't get a remainder of 0, I would know I must have made a mistake somewhere in my synthetic division, and I can go back and try to find that and fix it. Because that x equals negative 2/3 is a ZERO, I know that I'm supposed to get a remainder of 0. The 39, the negative 27, and the 3 are going to allow us to build our quotient. So the 39 is our constant term, the negative 27 is for our x, and the 3 is for our x squared. That gives us our quotient. And if you were paying attention as I was scrolling my screen, you saw that that's going to be a little bit of aggravation for us to solve the rest of the way through and give those other ZEROs, because that's going to be something that I can't do anything more than factor out of 3 before I'm stuck with having to bust out the quadratic formula and work through that, simplifying down and getting these two other ZEROs that have some yucky looking square roots in them. Now, I mean, they're not terrible, but they're not as nice as other kinds of ZEROs that we might come across. But that sort of stuff can still happen. And so we had this earlier example, all these nice ZEROs and nice x-intercepts. And then this example right here, and there's one nice ZERO, and then two other ones that are not so nice, which means I got one nice x-intercept that matches up with this ZERO, and two other x-intercepts that don't end up being very friendly looking. There's just too much stuff that can happen, and that's just, again, two examples that are cubics that have the powers of 3 showing up. Shoot, what if that's a higher power? Things could certainly seem to get way more complicated, and guess what? They definitely can get way more complicated. So it is very, very much of a challenge to try to talk about these other polynomials in the same sort of nice way and have such nice features and characteristics as what we saw with lines. Lines have slopes, cool. Parabolas have vertexes and cool, you know. Man, this is just not nice stuff that can always happen with these other polynomials. And this is still not all that we might be interested in. This is just ZEROs and factors. What else maybe is there going on? Well, you see you've got this thing at the bottom here peeking up. The fundamental theorem of algebra. It's a very short, and you might even feel by now that this is a pretty understandable kind of comment to make. Deceptively simple. As it turns out, this was an incredibly difficult thing to prove, but it has been proven. Any polynomial has at least one complex number ZERO. Now, we don't have to worry about some kinds of polynomials. We get to worry about some of the nicer ones. So here are some other things that we have. Let's just make a quick tweak to this fundamental theorem of algebra. We have the great fortune of dealing with things that are a little bit nicer. So our polynomials we're actually going to be dealing with and having to work with, they're going to have at least two complex ZEROs. Our complex ZEROs are actually going to always come in pairs. Remember, complex numbers also can tie in to real numbers. So when we say complex, that means not only complex numbers like a plus bi, but that also means stuff just like x equals negative 2/3. still a complex number, officially speaking. There's a result that's called the rational zero theorem, which can help us find a short list, not always actually short, just a shorter list of potential zeros for a polynomial. And that would be based on I don't have a good one to point at. It would be based on the first term and the last term of the polynomial, the factors of that first term and last term. The more factors that there are, the more different possible zeros we might have. Again, if we had a bunch of these that we were trying to test out, then the synthetic division would be the nice way to try to do that, because long division is long. So we fortunately get to kind of brush past having to deal with that. So we're not going to discuss the ins and outs of that rational zero theorem, but we do have a bit of other stuff going on that we are not necessarily quite as focused on. To worry about stuff that we can do much more reasonably, multiplicity refers to how often a factor or a zero occurs in a polynomial. We're going to see an example of that in a moment. We also have this result that's called the N Root Theorem. We've used the jargon degree before. The degree, the highest number of our exponent that appears. Usually it's going to be in the first term, but not always, because sometimes they like to try to catch us sleeping on the job. So if we've got a polynomial that has a degree n, then our polynomial has n total zeros, and that's taking into account any of the multiplicity stuff that's happening. So if I've got a zero that appears not just once, but twice, I count both of those towards adding up to the degree. So taking into account the multiplicity. So you might say unique zeros, where we don't mention any repetitions, versus just zeros, where we are interested in repetitions, we are interested in multiplicity. So then we can also say, with some of the terminology that we have, the polynomial has n roots, or the polynomial has n solutions. Since we've talked about how this stuff with the zeros ties in with x-intercepts, then we could say that if we're, again, counting repetitions, that n x-intercepts, that's a little bit weirder to talk about, because we think about the x-intercept and we go, there's a point or there's not a point, there's not multiple points that are layered on top of one another. That's a bit on the weirder side of things. Let's look at an example here where we start tying in some of this new business about multiplicity and roots and factors and zeros. So we've got this nice kind of idea. We love it when polynomials break apart into factors. Hey, let's look at something that's already factored. And my, oh my, is there a lot going on here. So we've got all these different factors. They're all color-coded. So we can start by listing those. And each factor has a corresponding zero. So the very first factor that we have listed is the x. If we take our factor and set it equal to 0 and solve for x, we get the zero. Well, x equals 0. There you go. Now let's bring in this multiplicity. How often did the factor x show up in the original polynomial? Well, that's just a fancy way of referring to what is the power that's attached to that factor. That's a 3. That multiplicity that we've got showing up there for that particular factor and that particular zero is a 3. Now we're only worried about what it is. We will, in just a moment, talk about what that can tell us. So let's just write it out. The next thing that we see showing up in our polynomial is this dark red factor of x minus 1. So that's the factor. If we set that factor equal to 0 and solve for x, that gives us x equals 1. That is our ZERO. And then we say, all right, what about the multiplicity? Do we have a power that shows up attached to that? Well, we do. It's power of 2. So the multiplicity is 2. And we can keep going through that collection of factors, taking note of all of those same kinds of things. So our next factor is x plus 5. Set that equal to 0. Solve for x. X is equal to negative 5. And what is the power attached to the factor x plus 5? That's a power of 3. So the multiplicity is 3. And so on, and so on, and so on. And then one more. And set equal to 0, solve for x. What's the power? So now, let's bring in this N Root Theorem. If we take into account all of the repeated factors, 6 of these, 4 of those, 3 of those, 2 of those, 3 of those, we add up all these multiplicities, that's something worth knowing about. So if we add up all of those multiplicities, we get 18. This is what this N Root Theorem is telling us. We've got 18 as our total number of ZEROs. So we're counting the ones that repeat. So x equals 0, x equals 0, x equals 0 again. X equals 2, x equals 1, x equals 1 again. Right? X equals negative 5, x equals negative 5, and x equals negative 5. Well, not only did the 18 total zeros happen, but the ZEROs are tied back to these factors, so 18 is the total number of factors. Well, if we take those factors and multiply them out, that means that the nastiest looking term that would show up would be an x that had a power of 18. And 18 then is our degree. If we take into account all of the multiplicities, all of those repetitions, then that's going to link us up with the degree. So we've got that connection there. Now that's just one connection to that multiplicity. As it turns out, there's a little bit more stuff that's going on. Here's something that I mentioned though already, and that is we're already dealing with nicer kinds of polynomials, ones that are going to have complex numbers that come in pairs. They're going to come in conjugate pairs specifically. So a plus bi is a ZERO. Guess what? A minus bi also going to be a ZERO. They're going to come in pairs. So if we wanted to build a polynomial, not just take one apart, we're going to build it now. We can go in both directions. There's versatility here. We're going to build a polynomial. It's got degree 3. That means that it's going to have 3 ZEROs. Maybe not a helpful comment. 3 factors, more helpful. They only give us 1. They give us a ZERO. So one of our ZEROs is this 1 minus 3i. We're expecting to have a total of 3 ZEROs, but they only told us 1. But that is a complex number and has to have its conjugate pair coming with it. The conjugate pair would be, in this case, the 1 plus 3i. So another 0 that automatically has to show up is going to be that x equals 1 plus 3i. Now that third ZERO, it can't be a complex number, at least not one like an a plus bi style thing, because those had to come in pairs. So that other ZERO can be any real number. So we could pick anything that we wanted to. We could pick x equals 0, x equals negative 10, x equals 3 is what we're using in this particular example. So we can now build a little bit of that kind of table that we were looking at a moment ago. If we've got a ZERO, we can transform that into a factor. There are different versions of that factor depending on how you rearrange things. And we've got the other factor, and so again, depending on how you like to rearrange things. And x equals 3 is a ZERO, means x minus 3 is a factor. And, well, they tell us that we got to build the polynomial, so we're going to have to take those factors and multiply them together. Well, let's use the x minus 1 plus 3i and the x minus 1 minus 3i. Those are ugly, and unfortunately, those are still in need of being multiplied out because this is not a polynomial that we're used to seeing. We're not used to seeing stuff that would have these complex numbers that show up along the way. So if we multiply this sucker together, that means we would have an x squared, a minus x, a minus 3ix, another minus x, a plus 1, a plus 3i, a plus 3ix, a minus 3i, and a minus 9i squared. Good gracious, all of that coming from that multiplication. And that doesn't even bring in the x minus 3 yet. If we start simplifying things, we've got an x squared and a minus 2x. Our 3ix stuff is going to cancel out. Our 3i stuff is going to cancel out. We've got a plus 1, and we've got a plus 9. So that gives us a plus 10 showing up there. And again, we could multiply that out a little bit more if we needed to. So if we multiply that out a little bit more, that would give us x cubed minus 3x squared minus 2x squared plus 6x plus 10x minus 30. And so combining our like terms and getting a more standard looking polynomial, x cubed minus 5x squared plus 16x minus 30. And that would be our polynomial based on all that stuff. They're possibly going to ask you to do this kind of stuff to make you practice some of your earlier, more basic algebra skills of multiplying, of transforming ZEROs into factors. They're going to want you to work in both directions for stuff like that. So just be prepared for the possibility of having to do that sort of thing periodically with some of those exercises. Now, we're close to the end. The last bit of stuff that we want to bring into play has a little bit more to do specifically with those x-intercepts. So we've said ZEROs are tied in with factors, but ZEROs are also tied in with x-intercepts, which also means to complete that collection of relationships, factors are tied in with x-intercepts. Here's how the multiplicity ends up getting used. If there's an odd multiplicity with our factor, with our ZERO, then the x-intercept is going to show our polynomial crossing through. But if our multiplicity is even, then our polynomial is going to bounce off of that x-intercept. So it could bounce off, literally bounce, or it could bounce off as though you were throwing a ball at the ceiling. It'd go bounce off the ceiling, boink. Then also, there's a bit more to how the degree ends up helping us. We had this notion of, with the quadratics, our a value, which is that leading coefficient, ties in with, does our parabola open up or open down? And so when we get into these other kinds of polynomials, we've got to worry about the interplay between the leading coefficient and the degree. So we can have stuff that works like the quadratics, that if we've got a positive leading coefficient, our very far left and very far right ends will go up like our parabola does. Can't say what's going on in the middle, but if our leading coefficient is positive and our degree is even, those far left and right ends both going up. If it's a negative leading coefficient, that's going to pop those downward instead. So if the leading coefficient's negative and the degree is even, that's going to be both downward. Then we think about the line as the most basic version of an odd degree. And if our slope was positive, then our line would go down, up. And so what happens in the middle? Who's to say what happens in the middle if we start hitting the power of 3, power of 5, power of 7, but the ends are still going to do that same sort of thing. Down and to the left, up and to the right. If we change the leading coefficient to a negative, that would flip stuff around, flip it upside down specifically. And so up and to the left, down and to the right. What happens in the middle? Who's to say? Well, that's where our x-intercept and multiplicity and zeros and factors and such can come into play. So now let's bring this new stuff in and kind of wrap it up with some of our other stuff by saying, let's sketch the graph of our function f of x equals x squared, parentheses x minus 1, parentheses cubed, parentheses x plus 4, parentheses power of 4. To just create a list of what we want, y-intercepts, x-intercepts. Because we have that recent comment that x-intercepts can either have a cross through or a bounce off sort of behavior. Let's make a note about that. And let's also finally make a note about what is happening to the very far left and very far right. Let's start with the nicest thing. Nicest thing would be the y-intercept. If we plug in 0, then we get 0 for our function value, and that would mean that our y-intercept is the point 0, 0. And that also would correspond to the fact that our first factor is x, so the first zero is 0, and that means that the first x-intercept is the point 0, 0. That factor has a power of 2, and so the multiplicity is 2. And if the multiplicity is even, then that is a bounce situation. The next factor that we see is an x minus 1. Set that equal to 0, solve for x, x equals 1. That means we have an x-intercept 1, 0. The multiplicity would be based on the power, which is a 3, and that would be a cross through. Then we have the factor x plus 4. So we have the zero, x equals -4. We have the x-intercept -4, 0. It has a multiplicity of 4, so that means that it is going to bounce. the leading coefficient is positive. Just real quick, 1x squared, 1x to the power of 3 is 1x cubed, 1x to the power of 4 is 1x to the power of 4. 1 times 1 times 1, that's positive. If we add up the multiplicities, we can get the degree. So 2 plus 3 plus 4 is 9. 9 is odd. Since 9 is odd, that means that if we do still have the chart up there, if we go up to our chart, that would mean that we are looking at a positive leading coefficient, an odd degree. The left end will go down, the right end will go up. And so if we take a moment and color code things here, we can match them up. I kept the graph in here. So our 0, 0 is listed here in our drawing in blue. And our 1, 0 is listed in green in that drawing. And the negative 4, 0 is listed in red in that drawing. Our end behavior is in orange. And if we wanted to have some extra accuracy, we could get some extra points in between our x-intercepts. But what we should find is that in between the negative 4, 0 and the 0, 0, that's going to swale a little bit deeper than in between the 0, 0 and 1, 0 that we've got showing up there. How far down? Who's to say? We didn't bother to put any scaling on that y-axis just for laziness sake. This is just a very rough sketch based on the fact that we've got those intercepts, that cross-bounce behavior, our end behavior showing up. It's not bad. It could be better, but again, that would require some extra work, some extra number crunching for us to try to achieve a greater level of accuracy with that. We don't necessarily need to worry about that, but we're trying to get that sense of how things tie together. We can again take graphs like this and backtrack them to these kinds of things. We can say, based on this end behavior, our leading coefficient has to be positive, our degree has to be odd, because that's a pass-through, that's an odd multiplicity, that's an even multiplicity, that's an even multiplicity. So we could say that the way that this would have to work out, smallest multiplicity there could be a 1, smallest multiplicity there could be a 2, smallest multiplicity there could be a 2, and that means that our degree here could be a 5, smallest that could possibly be. Because it's got to be odd, it could be a 5, it could be a 7, it could be a 9, it could be an 11, so on and so forth. We've got that x-intercept, that x-intercept, that x-intercept. We can backtrack those into factors. We could build different possible polynomials that could match up with this. So there are things that we can pick out of the graph and then pull back into algebra, even though what we've seen in this example, and really what we've seen in a lot of the examples so far, is that we're talking about the algebra and trying to eventually tie that in with stuff that has to do with the graphing. So again, we do want to make sure that you're aware that you can go in both directions. Do algebra, get graph information, start with graph information, create algebra information. We've got to be able to go in both directions. We've got to make sure that we're aware of those kinds of connections. How is that all spiderweb together with those relationships? So make sure that you're keeping an eye out for that as you're using this stuff in your practice.